Hi everybody. Today I am going to discuss about static equilibrium and dynamic equilibrium. So in this regard we need to know these two things. One is static loads, another is dynamic loads. Here I mention static loads are constant with time and dynamic loads are time varying. Majority of civil engineering structures which are designed with the assumption that all applied loads are static. And we use displace method of analysis to get relations in terms of the equation of static equilibrium like this. Here this is external applied static force, and K, it is the stiffness resistance, and U, it is resulting displacement. And this totally we call it as a restoring force. Now, regarding dynamic loads and the equation of dynamic equilibrium, we need to look at this figure. Here we can see there is a symbol I put here as a earthquake, and this is ground motion. Already I put the direction as well as inertia forces. It is applied on the buildings. And due to earthquake, there is earthquake force which results from rapid movement along the plane of faults within the earth crust. And this sudden movement of faults, it releases great energy, but in the form of seismic wave. And that seismic waves are transmitted to the structure through these foundations, and it causes motion in the structures. And this motion through abrupt horizontally or vertically oscillations, it results three things that is most important for our this equation of dynamic equilibrium. And those three results are acceleration, velocities, and displacement in the structures. So let's write the equation of dynamic equilibrium. If we compare these two additional forces are added here in this equation. So what are these two forces? One is inertial forces, another is damping forces, and third one, it is same as this one. We know that it is restoring force, and this F, it is lateral dynamic force. Now let's move ahead to understand all these points in details. we will discuss inertia forces. It is the first term of equation of dynamic equilibrium, and this is mass, and u double dot, this is acceleration. This acceleration, it generates inertial forces. And these inertial forces, we can see it here, inertial forces. Also, we can see here ground motions. Now, these inertial forces are, by seeing this term, we understand, are proportional to the acceleration of the mass. That is why we have taken this term in equation of dynamic equilibrium. And another important point, if we look at the figure, we can see acts opposite to ground motions. See here, inertial forces acting in the right direction, ground motion is on the left direction. That is why acts opposite to ground motions. Now, here we found this term actually mass into acceleration, but inertial forces, it is very much significant. Why? Because it depends upon two important things. Two important things. One is the characteristics of the ground motion. Characteristics of the ground motion. Another is structural characteristics of structures. These two important points. I am repeating again, this inertial force, it depends upon two important things. One is the ground motion characteristics and the structural characteristics of these structures. Now, basic characteristics of structure and ground. So we found two things, basic characteristics of structures and ground. It is actually fundamental periods. That is why I have written here fundamental period of structures. What is that? 0.5 second for low to up to 4 stories, 1 to 2 seconds for tall buildings. This is fundamental period of structures. This is, as I told, characteristics of the structures in terms of fundamental periods. Now, if we think of fundamental period of ground, range is 0.5 to 2 seconds. So if we compare these two, it looks very close. So if it is very close, then question comes about to compare, because it is important. Why? To see the existence of the probability of quasi-resonance. This is important to know it. So let's move for second term. In the equation of dynamic equilibrium, it is this one, Cu dot damping force. Damping force. As we understood till now, that ground motion, it produces energy in the structures, but it is needed, or in other way I can say it is essential to dissipate this energy. How? Through internal friction within the structure. I mean, through internal friction within the structural members and non-structural members. Very important. And this dissipation energy, we call it as a damping. Very important point to understand. Dissipative or damping force are proportional to the velocity induced in the structures. Because by seeing this we understand that. And already I mentioned that here we have one important thing, this C. C means what? C actually damping coefficient. And this is velocity, already we know. So this is damping coefficient. So how to take the value? I mean, how to measure this? C is the damping coefficients. And the value of damping in structures, it depends on, say, on its component. I mean the structures, components, component connections, and the materials. And in practice, that is most important points, this damping effect, it is expressed as percentage of critical damping. Percentage of critical damping. Because whenever we go for doing any analysis in any structural analysis software, we have to put the value for this degree of damping. Because it is written damping, then we are putting say 5% or 6%. So that's why I mentioned here degree of damping for reinforced concrete, it is 5 to 10%. And damping effect, already I mentioned, it is expressed as a percentage of critical damping. We have to understand this point. Percentage of critical damping. So let's move for the third item. I mean this one, restoring force. Restoring force, as we know, it is actually Ku. I mentioned here it is Ku. Basically, restoring force is proportional to the deformation induced in the structure during seismic excitations. So I wrote here, restoring force is proportional to the deformation induced in the structures. And it is during seismic excitations. And the constant of proportionality, it is referred as stiffness of structure. We can see it here. And another important point, this is very, very important point. This stiffness, it greatly affects the structure's uptake of earthquake generated forces. Very important points. And here say K, this stiffness, it is affected by quality of materials, age and support conditions. Also, it is affected by cracking. So here we have UT, it is displacement, and FT we know it is the externally applied force. So I think we are very much clear about these three terms. Inertia forces, this was damping force, restoring force. Now we can bring some conclusion. It is like sum of all resistive forces. So what are those resistive forces? It is due to inertia, damping and stiffness is equal to external forces. Also we can write, if you look at this, it is second degree. This one, it creates the equation, it is a second order differential equation that needs to be solved for this displacement. And another important points I am mentioning here, this dynamic equilibrium equation, it is also referred to as an equation of motion for a single degrees of freedom system under a lateral force. Very important line, this one. It is an equation of motion for a single degrees of freedom system under a lateral force. And that's all for this. This static equilibrium and dynamic equilibrium. Thanks for watching.